Hey there. Today we're going to study the relationship between vectors and coordinate systems. Let's do it. Let's begin by drawing a two-dimensional coordinate system. Then let us draw a pair of points, A and V. A will be at the origin and V at coordinates x2, y2. Given those 2 points, we can draw the line segment AB. To get a vector from this line segment, we must get the coordinates from the endpoint and subtract the coordinates of the beginning point. For this particular case, the vector is x2 minus 0, y2 minus 0, or simply x2, y2. When a vector has its tail at the origin, it can be called a position vector. Why? Well, because the components of a position vector are the same as the coordinates of the point where the tip of the arrow is at, which is exactly what you need to track the position of a particle in space. Now, for the more general case. A vector won't always have its tail at the origin. It could actually be anywhere. So, for the next vector, point A will be located at x1, y1, and point B at x2, y2. Once again, we can see the line segment AB, and the vector corresponding to that line segment would be x2 minus x1, y2 minus y1. What about 3 dimensions? The procedure is exactly the same. Take 2 points and subtract component by component the beginning point from the end point. The only difference is that this time you'll have 3 components instead of 2. And for dimension n? Well, you guessed it, it's exactly the same. Take 2 points and subtract the beginning from the endpoint and you'll get a vector. Your vector will have as many components as the dimension of your coordinate system. In fact, please recall that the number of components of a vector is also called its dimension. And also remember that beyond dimension 3, we have no way of representing them geometrically. So now you know how to obtain a vector given 2 points. Now let's see what happens when we look at the same vector from a different coordinate system. I'll draw 2 coordinate systems and a vector. From the point of view of the second coordinate system, the beginning of the vector is located at point A with coordinates u1, u2, and the end is located at B with coordinates v1, v2. From the point of view of the first coordinate system, the origin of system O2 is located at point C with coordinates d1, d2. Now, how does vector W look like from system O2? Follow the same procedure as before, and you'll get components v1 minus u1, v2 minus u2. No surprises there. But what about from the point of view of system O1? We'll follow the same procedure, but the trick is getting the coordinates of point A and V from system 1. First, focus on axis x. You'll see that from O1 to point V, there's a distance of d1 plus v1, which is the distance from O1 to O2, plus the distance from O2 to B. Similarly, for point A, measure the distance from O1 to O2, plus the distance from O2 to A to get d1 plus u1. Next, focus on the y-axis. From O1 to A, you have a distance of d2 plus u2. And from point V, you'll get d2 plus v2. So now you know the coordinates of points A and V when looking at them from system O1. Finally, all you have to do is follow the same procedure as before. Subtract A from B, and after you simplify the resulting expression, you'll find that the vector W looks exactly the same. In other words, when 2 coordinate systems have parallel axes, the components of a vector don't change when looking at them from either system. So naturally the next question is, what if the axes aren't parallel? To illustrate that case, let me draw another 2 coordinate systems and another vector. To simplify things a bit, I'll draw the vector so that its direction matches the direction of axis x2. Focus on looking at vector v from the point of view of system O2. Since it's laid along the x-axis, It has no component on the y-axis, so its components would look like v1, 0. But now look at it from the point of view of system O1. You'll immediately notice that it has components on both axes. Its tail is located at A1, A2, and its tip at V1, V2, in which case you'll get components V1 minus A1, V2 minus A2. So in this case, the vector looks completely, absolutely different. I want to emphasize that the vector is exactly the same. It didn't change. What changed was its mathematical representation, or its components, if you will. In other words, the same vector can look different when seen from different points of view. In any case, we won't deal with rotations for now, but at least now you know why the local position of something you're tracking in your game can look completely different when seen from the world origin. Next, we'll define some really important vectors. They will have the directions of the x, y, and z axis, and they'll have a size of exactly 1. Hence, they're called unit vectors. In fact, we assign them a special name, the I, j, and k vectors. They're really important because they form a basis, which means any possible vector you could think of can be written by scaling and adding different combinations of those three vectors. Let me repeat this information, but this time I'll give you a small list of their properties. First, their size is exactly 1. Second, vectors I, j, and k have the same direction of axes x, y, and z respectively. Third, any vector you can think of can be obtained by scaling and adding different combinations of those three vectors. So that's why the set of all three of them is called a basis. We'll study them in more detail when we start getting into algebra, into vector algebra next episode. To wrap things up, I'd like to do a few numerical examples of everything we covered. If you follow the whole video, this example should be easy peasy for you. So I'm just gonna leave you with some relaxing music until I'm done. Don't worry if you didn't quite get the last example. We'll look at this in detail in the following episodes, where we'll be diving into some vector algebra. In any case, I hope you're looking forward to the next episode, and thanks for watching. See you soon.